Okay, so in this video I'll be recording solutions to the 2019 VCAA Exam 2 for Mathematical Methods. Exam 2 is a 2-hour paper completed with the use of a CAS calculator and with bound reference, so I've got my CAS calculator available here. The standard Maths Methods formula sheet is also provided, but obviously when you have access to your bound reference you probably refer to the formula sheet a little less. The exam comprises 20 multiple choice questions and then either 4 or 5 extended answer questions. In 2019 it was 5 extended answer questions. Okay, let's make a start. Instructions for section A, you should be familiar with those before you go into the exam. There's nothing crazy in the multiple choice instructions. You get 1 mark for a correct answer, 0 marks for an incorrect answer. You won't lose a mark for an incorrect answer, you just get no marks, and if you give more than one answer for any question, you won't get any marks, so answering just once. You must provide your answers on the answer sheet. It's a good idea when you're doing these practice papers to actually print out a copy of the multiple choice answer sheet and practice the process of having to translate your answers across. Don't wait till the end of the exam to fill out the answer sheet. Do it as you go. You will run out of time. Okay, let's get started on the questions. So question 1 is becoming reasonably standard for an early multiple choice question in exam 2, and that is asking you about period and amplitude or period and range of a trig function. So here we want period and range of f, and so the period is to do with the 2/5. Okay, that's a dilation by 5 on 2 from the y-axis. So period we often learn is 2 pi over n, so 2 pi divided by that value, which is 2 pi times the reciprocal of that value. Oops. 5 on 2, and so that is 5 pi. So period is 5 pi, so we can rule out D and E. Now, range is to do with both the vertical translation and the amplitude. So the amplitude in this case is 3, that's the number 3 out the front there, and there's a translation down by 2. It's down by 2. And so those two things go together to tell us about the range of the function. So the range, if we go down by 2, is going to be from -2 minus 3, so taking away the amplitude from the average value of the function, and then from -2 up by 3. So that's going to be from -5 to 1, and so therefore B is the correct response to question 1. Okay, question 2. The set of values of k for which x squared plus 2x minus k equals 0 has 2 real solutions. Okay, so it's a quadratic function and we're interested in the number of solutions, 2 real solutions, discriminant bigger than 0. Okay, so discriminant in this case is, well, in every case, is b squared minus 4ac. In this case, that is 2 squared minus 4 times 1 times c, which is negative k, and so that is 4 plus 4k. And that has to be bigger than 0 for us to get 2 real solutions. So subtracting 4k from both sides and dividing both sides by 4. K must be bigger than -1, so therefore k is an element of -1 to infinity. So that is B. Okay, question 3. Let f be this function here, so it's a hyperbola translated to the right by 4, bit of a dilation. Don't know what A is, but it's positive, so no reflection. The average rate of change of f from x equals 6 to x equals 8 is, okay, so average rate of change being different from average value of a function. Okay, average rate of change is essentially change in y over change in x. So that's going to be the value of the function at 8 minus the value of the function at 6 divided by 8 minus 6. We can just get our CAS to do that for us. Just going to quickly define that function, and it is a divided by x minus 4, x minus 4, and so then we want f of 8 minus f of 6 over 8 minus 6, which is 2 obviously. So it is negative a over 8. E. Okay, question 4. That is equal to, now it's just a straight integral. We could try typing it into our CAS. I suspect usually they're not going to give you something quite as straightforward as you could just type it in your CAS and get the answer. And so therefore I suspect the form that the CAS will give the answer in is not going to match any of these. Oh sorry, there should be a plus in there. plus b times cos of x, but let's just see what it does. Sometimes you can still work from that, sometimes it's actually just much easier to do it by hand. Okay, it's not too bad. Okay, so what we've got here, it tells us, our CAS tells us that that is a times 1 minus root 3 on 2 plus b on 2. Okay, so that's going to be a times 2 minus root 3 over 2 plus b on 2. So that's a times 2 minus root 3 plus b all over 2. Are we close to matching something there? Yes, we are. 2 minus root 3 times a plus b over 2, so c. Okay. Other things you can sort of do is, press Control Enter here, get it as a decimal, just brute force your way through the options here, getting decimal approximations for those until you get something that matches, if your algebra is not strong enough to be able to work out how to simplify that to the point that matches an answer. Okay, question 5. Let f dash of x, so the derivative of f, be 3x squared minus 2x, such that f of 4 equals 0. The rule of f is, okay, so it's a very simple integration problem. So f of x is going to be the antiderivative of the derivative. So antiderivative of 3x squared minus 2x dx, which means adding 1 to the power gives us 3x cubed, dividing by that power is 3x cubed on 3, so it's just x cubed, minus 2x squared on 2, so it's just x squared, plus c, and that's what this is for. We've got a point, f of 4, when x equals 4, y equals 0. So f of 4, 4 cubed is 64, minus 4 squared, which is 16, plus c, and that has to equal 0. So 64 minus 16 is 48, plus c is 0, and so c must be negative 48. And so therefore our function is x cubed minus x squared minus 48. So C. Okay, question 6. A rectangular sheet of cardboard has a length of 80 centimetres and a width of 50 centimetres. Squares of side length x centimetres are cut from each of the corners as shown in the diagram below. A rectangular box with an open top is then constructed as shown in the diagram below. The volume of the box is a maximum when x is equal to. Okay, this is a pretty standard sort of, polynomials application question. So you've got to be able to understand though how the box is constructed. So essentially this rectangle on the bottom becomes the base of the box, and these sides all fold up to form the box that we're seeing here. Okay, so what that means is that this base here is that shaded bit of the net that I've drawn up there. So in terms of the length and width of the box, we need to be able to think about these dimensions here. Sorry, we need to be able to think about that and that. Alright, so that's not going to be 80, that's going to be 80 minus 2 lots of x, because there's x here and there's x here. Okay, and then this is 50 minus 2 lots of x. So on the actual box, that's the length and width of the base. And then the height of the box, if you think about folding up the sides, this x is going to give you the height of the box. Okay, so that means that your volume is x times 80 minus 2x times 50 minus 2x. You can obviously simplify that. There's common factors of 2 you can take out of both brackets and get, 40 minus x there and 25 minus x there, but it doesn't really matter. We're looking to find where the volume of the box, the value of x that makes the volume of the box a maximum. Now, you could graph that function on your CAS, you could solve the derivative of that function equal to 0 on your CAS, you could use function max on your CAS, all those things available to you. So I'm going to define my volume function. It is, again, don't need to have simplified it. I might have made a mistake when I simplified it, so why don't I just stick with the equation I got directly by multiplying the 3 lengths together. Okay, so there's our volume function in terms of x. As I said, you can graph it. Personally, I find I generally avoid mucking around in the graphing screen. I'm going to have to adjust the window, I'm going to have to do my lower bounds and upper bounds. It's all very ugly. I usually wouldn't bother. I would do it simply algebraically. So that would be either by solving the derivative of it with respect to x of v of x equal to 0 to get the coordinates of the stationary points. You would probably then need to think through which one gives you a minimum, which one gives you a maximum, hence the advantage of using function maximum will specify which one's a maximum. So function maximum, although the problem we'll have with this, let me just type this in and show you what I think is likely to happen, is it'll tell us it's when x equals infinity, because this is a cubic graph. So the maximum happens up here, whereas we actually want the derivative equals 0. So if that puts my derivative equal to 0, I can think through myself that this is a positive cubic, because by the time I expand it all out, I'll have positive x to the 4x cubed, sorry. So it's going to take this kind of shape. So therefore, the smaller of the two x values that I found back here, which is 10, 100 on 3 is about 33, that's going to be that point, which is the maximum, and this one's going to be that point, which is the minimum. Okay, so combining your CAS together with some logic, or you give a domain restriction here. If you think about your box, x is going to have to be less than 40 for that length to be true. It's going to have to be less than 25 for that to be true. Not true for that to be bigger than 0, and it's going to have to be bigger than 0. So you could give it the domain restriction from 0 to 25 if you need, and then it will give you the function max. Happens when x equals 10. Okay, so it doesn't ask you for the function max. Just to be clear, I bet the maximum value of the function is an option. Oh no, they haven't tempted you with that one. So the volume of the box is a maximum when x is equal to 10, so A. Okay, question 7, the discrete random variable x has the following probability distribution. The mean of x is, okay, so in 2020 you won't be doing this question. It's on discrete random variables, which were removed from the adjusted study design due to COVID in 2020, but I'm going to complete all the questions regardless. So mean of x, we simply multiply each x value with its probability. So expected value of x is 0 times a plus 1 times 3a plus 2 times 5a plus 3 times 7a. Obviously your CAS can help you if needed, but to be honest, simply being able to write down 3a plus 10a plus 21a and add them together yourself is quicker. 13 plus 21, so 34a. Sorry, we need to actually find a first, because we can find a from that. We know that all the probabilities, a plus 3a plus 5a plus 7a, have to add to 1, so that can give us a. So what have we got there? 16a is 1. So a is 1 on 16. And so therefore our expected value of x is 34 on 16, which is 17 on 8. So D. Alright, question 8. An archer can successfully hit a target with a probability of 0.9. The archer attempts to hit the target 80 times. The outcome of each attempt is independent of any other attempt. So binomial distribution, that's what that's all telling us. Given that the archer successfully hits the target at least 70 times, the probability that the archer successfully hits the target exactly 74 times, correct to 4 decimal places, is. Okay, so we've got h is the number of hits, and h is a binomial variable, where n is 80. He attempts to hit the target 80 times, and he can successfully hit the target with a probability of 0.9, so p is 0.9. Okay, define your variable. We want the probability that h is equal to 74, given that h is bigger than or equal to 70. So given that he hits the target at least 70 times, what's the probability he hits it exactly 74 times? So we need the intersection of those two things. So if he hits it exactly 74 times and at least 70 times, so that's just exactly 74 times, over the second thing in the conditional probability, which is h greater than or equal to 70. Okay, so menu 5 binomial PDF is fine, so A for the numerator. Number of trials is 80, probability of success is 0.9, the x value we want is 74. Okay, so that's 0.1235 over, okay, so menu 5B to work out the denominator probability. So n is 80, p is 0.9, we want at least 70, so lower bound is 70. It's not greater than 70, so it's at least 70, so it includes 70 up to 80. Okay, so that probability is 0.8266, and we're going to divide those two probabilities, so that divided by that. No reason not to work exactly with your CAS, and so we have 0.1494 correct to 4 decimal places, so C. Okay, question 9. Point AB is transformed by these transformations. The image of AB is 0. If the image of AB is 0, 0, then AB is. Okay, so if we multiply out this matrix equation, Txy means the transformed version of x and y. So I always call that x dash and y dash, the image of x and the image of y. If we multiply out the matrices, we get half times x plus 0 times y, so we get half x, and then there'll be this minus half on the top row, and then we get 0 times x times negative 2 times y, so negative 2y, and then we've got this minus 2 here. Okay, so we know that x dash is equal to half x minus half, and we know that y dash is equal to half x, negative 2y minus 2. Okay, so what that means, that these transformations tell us that every point xy becomes the point, or is transformed to the point, or is mapped to the point, half x minus half, negative 2y minus 2. Now, the question tells us that AB becomes 0, 0. So we know that AB will become half a minus a half and negative 2 b minus 2. And we know that this has to be 0, 0. So we know that half a minus half is 0, which means that half a equals half. Multiplying both sides by 2, a is 1. And we know that negative 2b minus 2 is also 0. So negative 2b equals 2, b equals negative 1. So a must be 1 and b must be negative 1, and so therefore the point must be 1, negative 1. So E. Okay, question 10. Which of the following statements is true for f of x equals x plus sine of x? Okay, so we might want to have a look at this just to see what's going on here, because it's asking us a lot about the graph and various things. It may not be a function you're particularly familiar with. You would need to sort of use addition of ordinates to think through what that looks like. So let's draw it on our CAS and have a look. So x plus sine of x. Okay, it looks something like that. I might make that 4 pi. Might make the pi on 2, just so I can get a bit of a sense of what's happening with the scale. Oops, 4 pi. Okay, so maybe even if we change that a bit, just to have a look at a bit more of it. Okay, so if you wanted to, you might also sort of draw the lines y equals x and y equals sine of x. So you can see that sort of addition of ordinates thing where the sine graph is now being centered around the line y equals x rather than around the horizontal x-axis. So that's the sort of shape we've got going. So the graph has a horizontal asymptote. No, there's no asymptotes at all here. Sine graphs don't have asymptotes. There are infinitely many solutions to f of x equals 4. Well, you could test that. You could solve f of x equals 4 with your CAS, but actually we can see what's happening here. If I were to draw a horizontal line at x equals 4, or if I were to even just get my CAS to draw in the line x equals 4, it's not going to cross with that blue graph infinitely many times. It's only going to happen once. Okay, so that's not true. F has a period of 2 pi. Now sine of x has a period of 2 pi, but this isn't periodic. It's not exact. We're not seeing the exact same thing repeat every 2 pi. So if I look from 0 to 2 pi and then from 2 pi to 4 pi, okay, it's the same shape, but it's translated up. It's not just simply repeating. So what you'd need to see for periodic is exactly what happens in here. So it looks something like this between 0 and 2 pi. You'd need to see that same thing repeating again, whereas that thing repeats but up there. So it's not actually a periodic function, even though there is some element of periodicity to it. Derivative is greater than or equal to 0 for all x equals r. That looks like that might be true. If you think about that, positive gradient or zero gradient everywhere, we could test those things easily enough. Solve derivative with respect to x. Now I've drawn that function as f1 of x. Never type a function into your equation more than once. If you drew the graph first, you can use the f1 of x, f2 of x, or define it in your cas first. You can use that over in the graph. I said equal to 0, so sorry, let me make it greater than or equal to 0. Now, sometimes your cas isn't very good with inequalities involving the trig, so let's just see what happens. Yeah, it confirms that that's actually true. So that's going to be true for all x values. We can also rule out f dash x, the derivative, as being cos x, because it wouldn't, the derivative of sin x is cos x, but there'd also be a 1. So that one's not true. So D is the correct response to question 10. A and B are events from a sample space such that the probability of A is P, where P is bigger than 0. The probability of B given A is M, and the probability of B given not A is N. A and B are independent events when. Okay, so if you know about independence, so generally speaking, probability of A given B is just probability, it's the same as probability of A given not B, which is just the probability of A. Okay? Now, in this case, we've been given conditional probabilities the other way around. So it's the same information to say that probability of B given A is the same as the probability of B given not A, which is the same as the probability of B. Okay. And so what that means is that this is pretty straightforward, really. That has to be the same as that. M has to be the same as N. So they're independent if M equals N. That's true. If you think about, if you tried to draw a tree diagram, you've got sort of A can happen or not happen, and then B can happen or not happen. Probability of A is P. Probability of B given A is M, so that's M there. This is therefore 1 minus P. This is 1 minus M. Probability of B given not A is N, so that's N there. That's 1 minus N there, therefore. So again, one of the, this rule is essentially saying that this probability is going to be the same as this probability if the events are independent. So that happens if M is equal to N. You don't really need to think through the other options. A is true and is correct, so we can go from there. You can muck around with a lot of other formulas. The other thing you can be looking to show for independence is that it means that the probability of A and B is the same as the probability of A times the probability of B. So you could have tried to work that out, but essentially it still reduces down to the fact that M has to equal N. Okay, question 12. If the antiderivative of f of x from 1 to 4, the integral of f of x from 1 to 4 is 4, and the integral of f of x from 2 to 4 is negative 2, then the integral of f of x plus x from 1 to 2 is. Okay, so we need a couple of things here. These two things together tell us about the integral of f of x from 1 to 2. Okay, so we know that the integral from 1 to 4 of f of x would be the same as the integral from 1 to 2 of f of x plus the integral from 2 to 4 of f of x. Okay, now we know that this equals 4. We don't know what that is, but we know the integral from 2 to 4 is negative 2, so minus 2. And so therefore we know that the integral from 1 to 2 of f of x is 6. Okay, so we're going to need that. Then we want to actually figure out this integral. So we want the integral from 1 to 2 of f of x plus x dx. So that is the integral from 1 to 2 of f of x, which we now know is 6, plus the integral from 1 to 2 of x, which we can work out. So this is 6. This is x squared on 2 from 1 to 2. This is 6 plus, so subbing in 2, 2 squared on 2 is 4 on 2, so that's 2. Take away subbing in 1 is a half. So we have 6 plus 1.5, or 3 on, sorry, 2. I said 6 and I wrote 2. 6 plus 1.5, or 3 on 2. Okay, so that would be 7.5, or 6 is 12 on 2 plus 3 on 2, so 15 on 2. So E for question 12. Okay, question 13. The graph of the function f passes through the point negative 2, 7. If h of x is equal to f of x on 2 plus 5, then the graph of the function h must pass through the point. Okay, so here x on 2, that means we've got f of half x. That's a dilation by a factor of 2 from the y-axis. And this plus 5 is up 5. Okay, so that means any point x, y, if we dilate it by a factor of 2 from the y-axis, we're doubling the x-coordinates, and up 5, we're adding 5 onto the y-coordinates. So if we have the point negative 2, 7, and we apply these transformations to that, negative 2 times 2 is negative 4, and 7 plus 5 is 12. That becomes the point negative 4, 12. So if f goes through negative 2, 7, then h is going to go through negative 4, 12, which is C. Okay, question 14. The weights of packets of lollies are normally distributed with a mean of 200 grams. If 97% of these packets of lollies have a weight more than 190 grams, then the standard deviation of the distribution correct to one decimal place is. Okay, so we've got, W is the weight in grams. W is a normally distributed variable. The mean is 200 and the standard deviation is unknown, so the variance is unknown. What we do know though is the probability that the weight is more than 190 grams, that is equal to 97%, so 0.97. And we want to use that to find the standard deviation. When we only have the mean or the standard deviation unknown, our CAS can solve an equation involving Normalcdf, so we'll do that. Menu 3.1. And then menu 5.5.2, Normalcdf. Okay, lower bound is 190, upper bound is infinity in a normal distribution. The mean is 200, and the standard deviation is what we don't know. I'm going to call that S. Now, my CAS won't like having an unknown in that box. It'll give me an error, too few arguments, etc., etc. Okay, that's fine. We want that probability to be equal to 0.97. And we want to solve for S. Now, when you're solving for the standard deviation, if it was just the mean, you could hit enter at this point and you'd be fine. If you're solving for the standard deviation, you need to tell the CAS that standard deviation has to be positive, or else it can't do it. Okay, and there we go. We find the standard deviation is approximately 5.32. So, B. Question 15. Let f be this quadratic function, x squared minus 4x plus 2. It's got a restricted domain. F of 5 equals 7. The function g is the inverse function of f. G dash at 7 is equal to. Okay, so essentially what we have here is we have some sort of parabola. It's got a restricted domain. I suspect that restricted domain is at the turning point. If we complete the square for that function, it should probably confirm that for us. X squared minus 4x plus 2. Comma x. Yep, so turning point is at 2, negative 2, sorry. Okay, so we've only got the right-hand side of this. Okay. And we know that the function f of 5 equals 7, so it goes through the point 57. Alright, then we want to know something about the inverse function. So the inverse function would go through negative 2, have its turning point negative 2, 2, and it would go through 7, 5, wherever that is. Okay. So the question is asking us about the derivative at 7 of the inverse function, which would mean the gradient at this point. And that's going to be connected to the gradient at this point, because when we find an inverse function, we're reflecting in y with x, we're swapping the x and y values. So if we swap x and y values, when we're talking about gradient, we're swapping rise and run. Okay? So if the original gradient, is m, which is sort of rise over run, just for the tangent, then the inverse gradient will actually be run over rise, because you swap the x and y values, so it'll be 1 on m. Not negative 1 on m, it's not perpendicular, It'll just be the reciprocal. Okay, so therefore, we don't actually need to find the inverse function here. We just find what the gradient is at this point, and then take the reciprocal of that for the gradient of the inverse function at this point. Okay. All right, so we can find f dash x, get our calcs to do it, but it's a quick and easy derivative by hand. And we want f dash at 5, which is going to mean 10 minus 4, which is going to mean 6. And so that means that g dash at 7, which is the same point, mirrored in the line y equals x, will be 1 on 6. So A. Okay, question 16. Part of the graph of y equals f of x is shown below. Looks like a quartic. The corresponding part of the graph of f dash x is best represented by. Okay, so if I think about this as being a quartic function, then I know that the derivative is going to be a cubic. Okay, it might not be a cubic because this could be degree 6, and this could be a, this could be the function. So don't know about the dilation. It could be, could be x squared times x minus 6. That would make it a, it's not x squared, it's x cubed. That would make it a quartic function, but it could also be x to the power of 5 times x minus 6, so a degree 6 polynomial. It could be x to the 7, so a degree 8 polynomial. So we only really know that the derivative is going to be an odd degree polynomial. If we think about what's happening here, so we know we have 0 gradient at 0, 0, so when x equals 0, the gradient will be 0, so it should also go through the point 0, 0, which all of these do. And we know that it's got negative gradient before and after that. Okay, so it should be below the x-axis, then just at the x-axis at the origin, and then below the x-axis again. So from that we can rule out B, we can rule out D, and we can rule out C. So we're down to A or E. Okay, and then the next point of 0 gradient isn't at 6, it's at 5. So we have 0 gradient at 5, which means we should have an x-intercept at 5, which is what we're seeing here in option A. Okay. All right. If worst comes to worst, just make up an equation for it. Just say, okay, well, that's the equation, and then calculate the derivative of that and get your calcs to draw it for you if you need to, just to get a sense of the shape. Okay, question 17. A box contains n marbles that are identical in every way except colour. So same weight, size, etc. So you're not more likely to pick out a bigger one, or everything's equally likely. So they're identical in every way except colour, of which k marbles are coloured red and the remainder of the marbles are coloured green. 2 marbles are drawn randomly from the box. The first marble is not replaced into the box before the second marble is drawn. Then the probability that 2 marbles drawn are the same colour is. Okay, so let's see what's happening here. So we can have a red or a green marble at our first selection, and then we can have red or green at our second selection. Alright, n marbles, k of them are red. So the probability of drawing a red marble in the first selection is k over n. Sorry, my r's all look a bit like k's there. And so that means the remaining marbles are green, so that's n minus k green marbles out of n marbles. Okay, then if we draw a red marble first, we now only have k minus 1 red marbles left. So we have k minus 1 red marbles out of, we only have n minus 1 marbles left in the jar or box or whatever it was, box. Green marbles, we still have the same number of green marbles, which was n minus k, divided by the new total of n minus 1. Alright, if we drew a green marble first, we have n minus 1 marbles left, so our denominators are going to be n minus 1. We haven't changed the number of red marbles if we drew a green marble, so we still have k red marbles, but we have n minus k minus 1 green marbles. Okay, we want the probability that the 2 marbles are the same colour, so we want that branch and we want that branch. Okay, so we want probability of red red or probability of green green, which means it's going to be k on n times k minus 1 on n minus 1 plus n minus k times n minus k minus 1 on n minus 1. I suspect that's pretty much D, just written with a common denominator. You might be able to see that from there. Multiplying together you get k times k minus 1 over n times n minus 1 plus, here we get, sorry, n minus k times n minus k minus 1 over n times n minus 1. And so obviously then we can just write that whole numerator together because we've got a common denominator. And so yeah, that's what's happening in option D. Okay, question 18. Distribution of a continuous random variable x is defined by the probability density function f, where f of x is equal to p of x from negative a to b, and we have a picture of y equals p of x, which comprises two linear functions. Now this question isn't relevant in 2020, where continuous random variables were removed from the course with the adjustments for COVID. So if you are watching this in 2020, you can skip past this one. Okay, it's known that the average value of p over the interval from negative a to b is 3/4. The probability that x is bigger than 0 is. Okay, so we've got two unknowns here, a and b, so we're going to sort of need two equations. So we need to use the fact that if this is a probability density function, the total area under here is going to be 1. So these are nice triangles and trapezia, so we wouldn't bother too much with integrals here. Okay, so we know that that bit of area there, so obviously it's a triangle, that distance is a, okay, and that vertical distance is 2a. So that bit of area is half times a times 2a, so that's just going to be a squared. And then this bit of area here, it's a trapezium, so it's going to be half times the sum of the parallel lengths, so that is 2a plus b, and then times the height, which is this distance along here, which is b. Okay, so we have, however we want to write that, b times 2a plus b over 2. Alright, so we know that the total area has to be 1. So the area is a squared plus b times 2a plus b all over 2, and that has to equal 1. Okay, so if we multiply by 2, we've got 2a squared plus, I might expand those brackets out there, with 2, we've got 2ab plus b squared, and that has to equal 2. Okay, so we'll just leave that. Let's just call that equation 1. We need another equation involving a and b, and that's going to be to do with this information about the average value. Okay, so if we know that if we're going to find the average value of a function, we do 1 divided by, so if it's over the interval from b to negative a, it's going to be b minus minus a, and we're going to integrate from negative a to b the function, and that it tells us in the question that that has to equal 3/4. Okay, so the useful thing here is that that integral represents the area under the curve, which we know has to be 1 because it's a probability density function. Okay, and so therefore actually this equation is quite nice because this is just 1 over a plus b equals 3/4. So we can tidy that up however we want, but we've got a cas, so we don't really need to worry about it. We can just solve those two equations for a and b. Menu 371, two equations, a and b are the variables, and we have 2a squared plus 2a, now careful with that, 2a times b, make sure you, if you're multiplying together two non-numeric characters, that you explicitly write the times. B squared, and that equals 2, and then our other equation is that 1 on a plus b equals 3/4, or a plus b equals 4/3, same thing. 1 on a plus b equals 3/4. Okay, so I think we know, what does it tell us? A and b are both positive real numbers, so we can ignore the one where a is negative root 2 on 3 and b is whatever. Or, let's see how many other options we've got. So we've only got the two options. So we want this one where a and b are both positive. Now I know that's got a negative sign in front of the b, but that's negative root 2 plus 4. Root 2 is smaller than 4, and so that's still going to be a positive number, even though it's written with a negative sign in the front of it. Okay, so this means that a is root 2 on 3, and I never factor out those negatives, so b is 4 minus root 2 on 3. Okay, and then we want the probability that x is bigger than 0. X is bigger than 0 is just this area here that we worked out already. We've got that expression there, so we can simply just sub our a and b values back in there. So probability that x is bigger than 0 is just that, 2ab plus b squared all over 2, and we can put these into that and work out what that is. So let me type that out. I might just write the half out the front instead of trying to do it all over 2. So it's going to be half times 2 times a times b. So a is root 2, root 2 on 3. So that's, 2 times root 2 on 3, and then we're going to do times b, which is 4 minus root 2 on 3, and then we've got plus b squared, so plus 4 minus root 2 on 3 squared, which is 7 on 9, so D. Okay, and then question 19. Given that tan of alpha is D, where D is bigger than 0, and alpha is somewhere between 0 and 2 pi, the sum of the solutions to tan of 2x equals D, where x is between 0 and 5 pi and 4, in terms of alpha is. Okay, so if we just have a think about this first bit of information here, okay, so tan of alpha equals D, where D is bigger than 0 and alpha is between 0 and pi and 2. So if we were to draw the graph of y equals tan of alpha and y equals D and think about where they intersect, tan of alpha only from 0 to pi on 2, so it's only actually half of the period of tan. So we're actually only getting, so this is alpha, that's x equals, not x equals, sorry, alpha equals in this case, pi on 2, we've got our tan graph, we've got y equals D, okay, and so therefore we've got just one solution there. And actually, if we think about that, if tan of alpha is equal to D, that means that alpha is inverse tan of D. Okay, so that's essentially how we can describe that point there. Inverse tan of D. Alright, then if we think about the other one, the solutions to tan of 2x equals D, where x is between that and that. So, x is between 0 and 5 pi and 4. So tan of 2x has a period of pi on 2, okay? So that means we're going to have an asymptote at pi on 4. X equals pi on 4, and then that will be pi on 2 there. And then we're going to have another asymptote at 3 pi on 4. And then that will be pi, and then we're going to have another asymptote at 5 pi and 4, and that's the end of the domain we're interested in. Okay, so it's a tan graph, so it goes, okay, and we want, again, when y equals D. Okay, so if we, like we did for this one, think about that first solution, we know that tan of 2x equals D, which means that 2x equals inverse tan of D, and we already know that that's alpha. Okay, so that means that 2x equals alpha, and so x equals alpha on 2. Okay, so this point here is alpha on 2. Now the next solution is simply going to be one period on from that, and the period is pi on 2. So this will be alpha on 2 plus pi on 2. And then this will be 2 periods on from that. So it'll be alpha on 2 plus 2 pi on 2, or pi. Okay. So the sum of the solutions, sorry I haven't given myself much room here, the sum of the solutions, which is what we want, the sum of the solutions is going to be alpha on 2 plus alpha on 2 plus pi on 2 plus alpha on 2 plus 2 pi on 2. And I'm leaving it as 2 pi on 2, so I've got a nice common denominator there. So we have 3 alpha plus 3 pi over 2, or 3 lots of alpha plus pi over 2, which is what E says, option E. Okay, and then question 20, the expression log x of y plus log y of z, where x, y, and z are all real numbers greater than 1, is equal to. Okay, so we're going to want to use some change of base here. So the change of base rule tells us that if we have log base a of b, that we can write that as log, and we can choose any other base we want, as long as we use the same base on the numerator and denominator, and be b up here and a down here. So we want to think about that. Now, the options I'm looking at here, most of these become fractions with numerators of 1. And so therefore, if I want to rewrite log base x of y as a fraction with a numerator of 1, given that I do log, don't know what base I'm going to choose yet, of y equals over log, don't know what base I'm going to choose yet, of x. If I want the numerator to be 1, I want that log base to be y. Okay, so this is the same as 1 on log base y of x. And the same logic tells us that log base y of z can be written as log base z of z over log base z of y, and so therefore it is 1 on log base z of y. And so these two things added together are equal to these two things added together. So 1 on log y of z plus 1 on log z of y, log y of x on 1 on log y of x plus 1 on log z of y. Okay, it's almost right here, except we've got these negatives, which we don't want. Log y of x plus log z of y, so D, sorry. So option D is the correct response to question 20. Okay, so that's the 20 multiple choice, and now we'll move on to the extended answer portion of the exam. Alright, so again, making sure that before you even walk into the exam, you're 100% familiar with the instructions. The standard instructions are the same every year. In particular, where a numerical answer is required, an exact value must be given unless otherwise specified. Where more than one mark is available, appropriate working must be shown, and diagrams not to scale, but these are the two main ones. Also worth noting, last year for the first time, so 2019 for the first time, you had to write using a blue or black pen, and that was because the exams are scanned for marking. Interestingly, the early cover sheets we've seen for the 2020 exams no longer mention the instruction for a blue or black pen, but I would find it hard to imagine that they're going to revert from scanning the exams, especially during COVID times when they would prefer, people to be able to access the papers remotely for marking. So I'd be prepared to write in a blue or black pen in 2020, and if you get in there and it doesn't specify that, then by all means you can write in a pencil. Okay, let's work through the extended answer question. So question 1 is worth 11 marks. We've done 20 marks worth of questions in the multiple choice, so there's 60 marks remaining in these 5 extended answer questions, so they should each average about 15 marks, so 11 mark question is a slightly short one, there'll therefore be longer ones. Okay, find the derivative of f, nice and easy, it's a product rule required. However, if you've got your CAS and it's an extended answer question where a function's defined right at the beginning, probably one of the first things I'm going to do is to define that function. So it's x squared times e to the negative x squared. Alright, we want the derivative, so shift minus. Okay, As I said, easy enough to do by hand. It's a nice product rule, but when you've got your CAS, there's no reason to do it by hand if you don't need to. So it's 2x minus 2x cubed times e to the negative x squared. State the nature of the stationary point on the graph of f at the origin. Okay, so again, because you've got your CAS, it's not asking you to justify or to do a sign diagram or to do anything like that. I'm just going to adjust my graph again. So if I just have a quick look at what this function looks like, f of x, we can see that looks like we have a local minimum. If I maybe adjust the windows here because we clearly don't need this much. Yeah, we seem to have a local minimum, or it's actually going to be an absolute minimum because they're asymptotes out to the left and right, so the lowest point on the graph. So essentially just the word minimum would be sufficient, a minimum turning point. Most precisely, it's actually the absolute minimum point of the graph. Minimum turning point, sorry. Okay, 2, find the maximum value of the function of f and the values of x for which this maximum occurs. Okay, so now that I can see my graph, it looks like the maximums occur when x equals plus or minus 1, but perhaps let's just solve our derivative equal to 0 to be clear on that. I often, if I'm doing extended answer questions, I will define the derivative as a separate function. I usually use the convention in my CAS. I define it as, if my original function was called f of x, I define its derivative as df of x. And we'll make that equal to that. Okay, just makes it easier to work with the derivative, particularly if you're trying to substitute into the derivative at any point. So solving the derivative equal to 0, derivative equal to 0, struggling, here we go, equal to 0 for x. We get x equals negative 1, 0 and 1, okay, and we already know that it's a minimum point at 0. So f dash x equals 0 tells us x equals negative 1, 0 or 1. And we know there's max when x equals plus or minus 1. So let's work out f of 1. You might want to just check it's the same for f of negative 1. It certainly is. Okay, so therefore we have max value is e to the negative 1 when x is equal to positive or negative 1. Okay, so answering the question, find the maximum value and the values of x for which this occurs. Maximum value is this at these x values. That's all the 2 marks would be for, so just make sure you fully answer the question. Find the values of d, where d can be any real number, for which f of x plus d is always negative. Okay, so let's go back to our graph over here. If we want the whole function to be negative, we would need to translate it down so those maximum turning points are below the x-axis, not on the x-axis, because that would be, then the function could equal 0, it wouldn't be always negative. So we want those points to be below the x-axis. Okay, so if you think about, you've sort of got this thing happening, that is the point 1 on root 2, sorry, not 1 on root 2, where'd that come from? E to the negative 1, okay? And so you're going to need to move the graph down by more than e to the negative 1 so that these maximum turning points are below the x-axis. Okay, so therefore d has to be more than e to the negative 1. Obviously you can write e to the negative 1 as 1 on e if you prefer. Same thing. Okay, part E, find the equation of the tangent to the graph of f at x equals negative 1. This is very simple with your CAS. Don't ever find tangents by hand in a tech active paper. So menu 4.9, tangent line, we want tangent to f of x, comma, when x equals negative 1. Okay, actually we could have thought that through ourselves. So it's y equals e to the negative 1. And that's because we already know, that there's a stationary point at x equals negative 1. So we already know when x equals negative 1, there's a stationary point, so the tangent will have 0 gradient, and that will be equal to the y value, which is y equals e to the negative 1. It'll also be the same as the tangent when x equals positive 1. You can check that if you're not convinced by that, because they're both the maximum points of the function. Okay, so we're looking at that sort of situation. Find the area enclosed by the graph of f and the tangent to the graph of f at x equals -1, correct to 4 decimal places. Okay, so again, let's just draw ourselves a rough sketch of what's happening here. So we go through 0, 0, we go through those, we get our asymptotic behaviour out here, and we've found the tangent is y equals e to -1. Okay, that was at x equals -1, that's at x equals +1. So we want to find the area enclosed by the graph of f and the tangent to the graph of f at x equals -1. So we're looking to find this area in here, so the tangent and the graph of f, the area enclosed by that. Okay, so that area is going to be the integral from -1 to 1 of the tangent, which is e to the -1, take away the function, which is f of x. You could also do 2 times the integral from 0 to 1, but given that you've got your CAS, it doesn't make it any easier to do that. If you're doing it by hand, I would do that, but okay. So make sure you use the proper e to the -1, or you could, of course, quicker, just go up and get that. Oh, sorry. Although that's a problem, isn't it? So you could press Control-C to copy that from there, and then Control-V so you can put it in the right place, or you could have just retyped it. And it's minus f of x. Shouldn't be typing out the function again, you've already defined it. And we want the area correct to 4 decimal places, so that is approximately 0.3568. Okay, so D, let Mn be a point on the graph of f where m is between 0 and 1. Okay, so m is going to be some kind of point on the graph there. Find the minimum distance between m and the point 0e and the value of m for which this occurs. Okay, so 0e is going to be somewhere out here. So we're trying to minimize the distance between those 2 points. Okay. Now m has coordinates of mn, which is m f of m. Okay, you don't need 2 variables there. So we want to find the minimum distance and the value of m for which this occurs, correct to 3 decimal places. Okay, so the distance, I'm going to call that d, is the square root of, so a distance formula, it's going to be f of m minus e squared plus m minus 0 squared. So I'm going to define that function. My distance in terms of x is going to be the square root of f at m. Sorry, actually it's not the distance in terms of x, is it? It's the distance in terms of m. F at m minus e. So f of m minus e squared plus m minus 0 squared. Okay, and then we want to find the minimum distance. So we want to find the minimum value of that function where m is somewhere between 0 and 1. So again, my CAS can just do that for me by doing function minimum. Okay, so we can do menu for 7, function minimum of d of m, comma m, and then outside here we'll need that restriction, given that m is somewhere between 0 and 1 inclusive. Given that it's a 3-mark question though, I would suggest that you want to be showing, I would still be writing the derivative, solving derivative with respect to m of 0, equal to 0, sorry. So actually we might just do a quick derivative, with respect to m of d of m is that, we don't need to write that down, but if we solve that derivative equal to 0 for m, okay, we get, now given that m can be between 0 and 1 inclusive, we get 2 solutions, okay, so we get m equals 0 and 0.7830 for m element of 0 to 1. and we already know because we did function minimum. So let's be clear, find the minimum distance between m and the value of m for which this occurs. Oh, okay. 3-mark question actually, I think, giving you distance function, and then it does ask you for two things. Sorry, so the minimum distance and the value of m. So we probably don't need this. We could probably just say min distance occurs when m equals 0.7830, so, sorry, 3 decimal places, so 0.783. And then min distance is equal to, so I'm going to sub that back into my distance function, so d of, I'm just going to type as many decimal places as I can see there, so I'm working nice and precisely, 0.78303367678. And the minimum distance is, correct to 3 decimal places, 2.511 units. Okay, question 2, also worth 11 marks, so a bit under the average of 15 marks across the 4 extended answer questions. Oh, sorry, we didn't have 4, did we? We had 5, so it should be 12 marks on average, so actually these are about right. An amusement park is planning to build a zip line above a hill on its property. The hill is modelled by this cubic equation here. I must say, one thing I really didn't like about this exam was that they didn't give you this as f of x or g of x or h of x or whatever, and it just made the notation really difficult in terms, you sort of had to write out more because you couldn't just write f dash x, you had to sort of write, sort of write out the derivative or write out the expression. It actually made it quite cumbersome to work from. So do be careful about that, because the first thing I am going to do is I'm going to define this function in my CAS, but I must be careful about not just referring to f of x on the paper when f of x actually hasn't been defined in the question. If you want to, you could probably say somewhere really clearly, let f of x be this, be 3x times x minus 30 all squared on 2000, so that then you can refer to f of x. But yeah, don't just magically start writing f of x in places if it doesn't actually exist somewhere. And I would generally say stick to the notation they've provided you in the question. Okay, so we've got the picture of the hill, we've got the equation, I've defined it in my CAS. We want to find dy dx, so shift minus, derivative of f of x. Okay, so that's that. Lots of different ways that you could actually write that. You might prefer to take that 9 on 2000 out the front, times x minus 30 times x minus 10, or any version of that. I might define my function, I might define my derivative as well while I'm here, so derivative of f with respect to x, derivative of f of x is that. Okay. State the set of values for which the gradient of the hill is strictly decreasing. Now, I thought this was a slightly mean question. Most people, students gave the answer that was to state the set of values of x where the hill is decreasing. Okay, so that would be from 10 to 30, and because it is strictly decreasing, that would be 10 to 30 inclusive. However, that's not what the question asks for. The question asks for when the gradient of the hill is decreasing. Okay, so that is when the derivative is negative. Not just when, when the gradient of when the derivative of the derivative is negative. So that's where that was a bit mean. So actually what you wanted to do was to solve where the derivative of the derivative is less than 0. It's actually less than or equal to 0 for strictly, but we'll just get this for now and interpret that. Okay, so that happens when x is less than 20. But as I said, it's actually when we do strictly decreasing, the derivative can actually be 0. You include the endpoints essentially because it's over what interval of values. So if we go back to this, sorry, I didn't mean to enter that twice there. If we go back to this original, let's say it was this one where we've got a nice clear graph that we can see. Strictly decreasing means that if you pick any two values within the interval from 10 to 30, the one on the right is lower down than the one on the left. Okay, so if I can include 10 in that interval then, because if I pick this point where x equals 10 and any other point, the point on the right is lower down than the one on the left. If I pick any point along with this point at 30, this 30 is lower down than this one on the left. So it's strictly decreasing from 10 to 30 inclusive. The hill is strictly decreasing. The gradient of the hill will be strictly decreasing where x is less than or equal to 20. Okay, so that is when x is an element of negative infinity to 20. Obviously, we can't include negative infinity, but 20 needs to be included because of the strictly decreasing. That was, yeah, a little mean. I think it would have been hard enough to ask you about strictly decreasing, just the hill, the 10 to 30. Okay, anyway, the cable for the zip line is connected to a pole at the origin at a height of 10 meters. So this is the pole here, okay, and is straight for x between 0 and a, and a is somewhere between 10 and 20. Okay, so we can shift around the point A. It could be down here, for example, in which case we do a straight line from there, pretend that was straight, and then we follow the hill shape from that point. The straight section joins the curved section at AB. The cable is then exactly 3 meters vertically above the hill from from A to 30, from x, where x is between A and 30. So as I said, if this was A down here, AB here, then we would have a straight line from there to there, and then we would follow the line that is 3 meters above the hill from that point onwards. Okay, as shown in the graph below. State the rule in terms of x for the height of the cable above the horizontal axis for x equals, x is an element of A to 30. So the cable is simply just 3 meters above the original hill, okay, and so that means the rule for the cable, I'm going to call it C of x, okay. So the cable is going to be C of x, and it's the original function, which I can't refer to as f of x because it hasn't been defined as f of x. So it's 3 on 2000 x times, sorry, let me just get it again, x minus 30 squared. Plus 3. Okay, in my CAS, I'm going to, not solve. In my CAS, I'm going to define the function for the cable so I can use it. C of x is f of x, which is how I've defined the original hill, plus 3. Great. Find the values of x for which the gradient of the cable is equal to the average gradient of the hill for x between 10 and 30. Okay, so we first need to know what the average gradient of the hill is. Okay, so average gradient, average rate of change. So the average gradient of the hill is going to simply be the same as the average gradient of the cable. So if you want, you could say it's going to be C of 30 minus C of 10 over 30 minus 10, because the average gradient of the hill and the cable should be the same. And given that I can use C of x where I can't use f of x, it's going to be a bit easier to write that down. So I'll confirm that for you. So if I use f of 30 minus f at 10 over 30 minus 10, we get an average gradient of negative 3/10. If I did that with c instead of f, just to be clear, because the only difference between c and f is a translation up, so the gradient is still the same, it's still going to be negative 3 on 10. Okay, so we're going to need that. Now we want to know the values of x for which the gradient of the cable is equal to the average gradient of the hill. Okay, and so therefore we want the derivative of the cable to be equal to negative 3 on 10, which is the same as the derivative of f being equal to negative 3 on 10. And I've already defined my derivative of f, so I'm just going to do that. Solve the derivative of x equal to negative 3/10 for x. And obviously x has to be between 10 and 30, and both of those values are between 10 and 30. Okay, so x is going to be equal to, now again, I hate the way the CAS factors that out. If you expand both of those out, you've got negative 10 times negative 6, which is positive 60 in the left-hand one, and 10 times 6, which is positive 60 as well. So it's positive 60, and then it's plus or minus 10 root 3 over 3. Okay, so it's just values of x, doesn't want coordinates. So there are two values of x where the gradient of the cable is equal to the average gradient of the hill. Okay. The gradients of the straight and curved sections of the cable approach the same value at x equals a. So that is, they join smoothly. Continuous smooth join at a. State the gradient of the cable at a in terms of a. Now there's two ways that you can answer this question E. And then whichever way you don't use in E part 1, you'll need to use the other one in E part 2 to create an equation that you can solve. So gradient of the cable at A in terms of A, let me go back to the graph. You can do two things. So you can simply just do rise over run. So AB would mean that it's A and then essentially F of A, which, you know, I've defined F in my CAS. So F at A would be that. Oh, but it's plus 3 because it's on the cable. Sorry, so it's actually C of A, which we have defined. So that's good. Okay, so actually we wanted C of A, which would be that one. Okay. So you could either do, the gradient at this point is either going to be rise over run from the straight line bit, straight line section. So that would be 10 minus C at A over 0 minus A, whatever that is. Or it's going to be the derivative of the cable, or the hill, doesn't matter, it's the same thing, the derivative of the cable at A. Okay, so one of those two things, and then the key thing is in the next part, you're going to be able to equate those two things to work out A. So the gradient of the cable at A could either be, as I said, C at A minus 10 over A minus 0, or it could be C dash at A. My instinct straight away was to go with the derivative one. So C dash at A. If I do the derivative of C, derivative with respect to x, respect to x of C of x, given that, which is why I tend to define my derivative functions, given that x equals A, it's going to be that. Obviously you could also have done the derivative of f at A, because the derivative of f and the derivative of c will be the same. If you expand that out, you get the same thing. So you can either write it as 9 on 2000, a minus 30, a minus 10, or that's the same as 9a squared on 2000 minus 9a on 50 plus 27 on 50. Or, as I said, you could have the expression that you get from doing, did I do it up here? No, I didn't. From doing the rise over run, 10 minus C at A over 0 minus A, which would give you that. Okay. So either any of those answers would be correct answers here. They're all the gradient of the cable at A in terms of A. And then you want to find the coordinates of A. So this is where you then want to think about taking those two different expressions for the gradient and making them equal to each other. So we know that the derivative at A is going to be the same as C at A minus 10 over A minus 0, which is the gradient of the straight line. And if we solve that, so if we solve our, sorry, I'm just going to get this expression. So that was our derivative of C at A. And if we make that equal to this, solve for A. And if we want to just be a bit more precise about that, so we don't have to filter through them all, we could give it the condition that A has to be somewhere between, I think A had to be between 10 and 20, didn't it? Yes. A has to be between 10 and 20 inclusive. A is between 10 and 20, we just actually get the one value. And we want correct to 2 decimal places. So we get A is approximately equal to 11.16 since it's between 10 and 20. Find the coordinates of A. Okay, so that's A, and then we're going to need the, we know that B is C at A, and so we're going to substitute that back in. So C at A, given that A is that. And so C is approximately 8.95, correct to 2 decimal places, and so therefore A is 11.16, 8.95. Sorry, I just realised I rounded that incorrectly. That's not 11.16, it's 11.12. The 5 tells us to round the 1 up to 2, not the 5 up to 6. Sorry, so that's 11.12. I used exact values in my CAS. There's no issue with the coordinates of the point. So, 3 marks there. I suspect 1 for some kind of equation, 1 for your A value, and then 1 for the coordinates. But yeah, coming up with the 2 different ways to describe the gradient at A, and then equating those 2 ways. So as I said, you could have had this as your answer up here, and then you would have equated what you had in part 1 to the derivative of C at A. Okay, part 3, find the value of the gradient at A, correct to 1 decimal place. Okay, so this is just going to be about working out C dash at A. So C dash at 11.12, okay, which is the same as F dash. So it's the same as my derivative of F at A, given that A is this value. And so correct to 1 decimal place, that's going to be negative 0.1. Okay, just 1 mark for that answer. Okay, on to question 3. Okay, so during a telephone call, a phone uses a dual frequency electrical signal to communicate with the telephone exchange. The strength F of a simple dual tone frequency signal is given by this function. T is measure of time and T is bigger than or equal to 0. Part of the graph of y equals f of t is shown below. Okay, so let's define our function. Defining f of t, f of t equals sine of pi times t on 3 plus sine of pi times t on 6. Okay, state the period of the function. Okay, so you might think it through algebraically. So if you've got pi on 3, the period of that is 2 pi divided by pi on 3, which is 2 pi times 3 on pi, which is going to be 6. And the period of this is going to be 2 pi divided by pi on 6, which with the same logic is 12. It needs to be the lowest common multiple of these, so the period will be 12. You don't, however, need to work that out. You can also see that from the graph that you're... Sorry, I nearly fell off my chair. You can also see that from the graph where you can see you've got a full period between 0 to 12 and then a second exact repeat between 12 and 24. So period is going to be 12. It doesn't give us units for the time. It just says t is a measure of time. So we can't write 12 hours or 12 minutes. It's just 12. Find the values of t where f of t equals 0 for the interval 0 to 6. Okay, so we can probably see that it's going to be 0, 4 and 6 from the graph. We've got our function defined though, let's be clear about that. Solve f of t equal to 0 for t, because it's a trig function we will need a restriction, given that 0 is less than or equal to t, which is less than or equal to 6. Sorry, times 0 instead of equals 0 there. Okay, there we go. So f of t equals 0 for t equals 0, 4 or 6. Now 0 to 6 inclusive means those solutions at 0 and 6 should be both included. Okay, find the maximum strength of the dual tone frequency signal corrected to 2 decimal places. Okay, so we want the maximum strength. We can see from our graph it's at this point here. So I might just do menu for 8 function maximum of f of t just over the first period, because then it'll be the same for every other period. So given that 0 is less than or equal to t, which is less than or equal to 12. What did it say? Correct to 2 decimal places. Okay, so then we actually want to work out the maximum strength. This is a 1 mark question. So f of t, given that t is this. Control enter, sorry. Okay, so the maximum strength. Let me just do this one to 2 decimal places as well. Okay, so we get max strength is, I don't think we have any units for the strength either. F is the strength, it doesn't tell us what that's measured in. So max strength is 1.76, and that happens when x is 1.79 to 2 decimal places. Sorry, not x, but t. Okay, but this is the answer the question asks us for. Find the maximum strength. Find the area between the graph of f and the horizontal axis for t is an element of 0 to 6. Okay, so let's just have a look at the graph. So we're looking at 2 regions here. We're looking at that integral, so positive integral from 0 to 4, and then the negative integral from 4 to 6. Okay, so the area is going to be the positive integral from 0 to 4 of f of t dt, plus the negative integral, so minus the integral from 4 to 6 of f of t dt. Oops. Rather than subtracting the integral, you might prefer to add the integral, but to switch the limits around, so 6 to 4 instead, same thing. Okay. So it doesn't tell us to round, so we should get an exact answer from this. So shift plus 0 to 4 of f of t dt, plus shift plus again 6 to 4, or you would have had it as minus the integral from 4 to 6 f of t dt, and we get 15 on pi. 2 marks there, so make sure you show the integrals that you've calculated to find the area and then actually give the area. Let g be the function obtained by applying the transformation t to the function f, where a, b, c and d are real numbers. Find the values of a, b, c and d given that the integral from 2 to 0 of g of t plus the integral from 2 to 6 of g of t has the same area calculated in part D. Okay, so I want to think about that that's a distance of 4, that's a span of 4, whereas this is only a span of 2. Okay, also these limits are reversed, so this is clearly an area under the x-axis. Okay, so this is clearly needs to be a lump of width 2 below the x-axis, and this one needs to be a lump of width 4 above the x-axis, so that those 2 integrals are giving you the same area as these 2 integrals. Okay, so what I mean by that is the second integral here, this one, the integral from 2 to 6 of g of t must be giving us that area there. That has to be equal to the integral from 2 to 6 of g of t, which means I need to get that lump so that it is happening between 2 and 6. Okay, so that has to be g of t. And then I need this bit of area here to be equivalent to the integral from 2 to 0 of g of t. I think that's what it was. Let me just go back and check. Integral from 2 to 0 of g of t, yes. So the limit's around the wrong way because it's below the x-axis, but it's going to be between 0 and 2. So we need to get that happening. Okay, so it's not just a case of translation, because if we were to translate this to the left by 4, you wouldn't be getting a big lump happening between 2 and 6. Okay, so there does need to be some kind of reflection happening here. Now, we could either take the original graph, change color, and reflect it in the x-axis, and if we reflect it in the x-axis, this bit up here would be happening in the correct order, and then translate it to the left by 6. Okay, so we could reflect in x-axis and then left by 6. Okay, or instead we could reflect the shape in the y-axis and then translate it to the right by 6. Now, the other thing is that the translations doesn't have to be by 6, because we know there's also a period of 12. So if we did it to left by 6, or by 6 plus 12, or by that plus 12, or by 6 minus 12, okay, so right 6 instead, they would all give us the same. So there's actually infinitely many correct answers to this question. I would obviously stick with the simplest ones. Why would you translate it left or right, left by 18, when you could translate it left by 6 and get the same thing? But one of these two combinations, so reflecting in the x-axis and then to the left by 6, or reflecting in the y-axis and then to the right by 6. I must say this was my instinct when I first did this question, but they both work. So if I wanted to do reflection in the y-axis and then to the right by 6, I need the x values to be negative. So I'm going to need a to be, so if I reflect in the, let me do it in the two ways. If we reflect in the y-axis, and then we need to go to the right by 6 when we do that. So the reflection in the y-axis means that x values have to become negative, so a would have to be -1. We don't want the y values to reflect, so b stays as 1. And to the right by 6 would mean that c equals 6 and d equals 0. So we don't go left, we don't go up or down. Okay. Or we could go reflect in x-axis and then left by 6. And so this would mean a has to be 1 and b has to be -1. Oops, sorry, -1. And left by 6 would mean c has to be -6. Sorry. But we don't want to go up or down, so d is 0. So either of those, and as I said, there's also the scope that, you know, these translations could be that plus or minus a period. So any of those would be correct combinations, but you have to give a completely correct combination. So for example, you can't have b equals -1 and then have it together with c equals +6, because that doesn't make any sense. All right. Okay, part F, the rectangle bounded by the line y equals k, the horizontal axis, the lines x equals 0 and x equals 12, has the same area between the graph of f and the horizontal x-axis for one period of the dual tone frequency signal. Okay, so we want to first of all think about the area between the graph of f and the horizontal axis for one period. Okay, sorry. So let's go back up to our graph again, which I've made a bit of a mess of. Let's get rid of all of that. So what we found in a previous part, we found these areas here. We found the areas between 0 and 6, remember? And they in total were 15 on pi. Okay. So if we want the total area between the curve and the x-axis for one period, we would also need those, and so it's going to be double 15 on pi. Okay, so 30 on pi. So we know that the area between f and the x-axis for one period is the answer we got up here in part D times 2. So 2 lots of 15 on pi, and so that is 30 on pi. Now we want the rectangle bounded by the line y equals k, the horizontal axis, and the lines x equals 0 and x equals 12 has the same area as this. So we want a rectangle, let me go back up here again. We now want a rectangle that is, you know, x equals k, y equals k, x equals 12, x equals 0, and the x-axis. So what we now want is this total area to be equal to the area of this rectangle, okay? And so therefore we want that green area to be equal to 30 on pi as well. Now that green area, that's just simply a rectangle with a height of k and a width of 12. Okay, so all we need is 12 times k has to equal 30 on pi. This is actually a really straightforward question. So we need 12 times k has to be equal to 30 on pi, and so that means k has to be equal to 30 on 12 pi, which is 5 on 2 pi. Okay, so 2 marks again. I suspect 1 for actually working out what the area between the x-axis and the curve for one period is, and then for working out what that means for k. Okay, question 4, 17 mark extended answer question. It's a probability question. Quite a lot of this question from memory is not relevant in 2020, but I will flag for you the bits that are relevant. The Lorenz birdwing is the largest butterfly in town A. The probability density function that describes its lifespan x in weeks is given by. Okay, so I'm going to define my probability density function. So these early parts of this question about the probability density function, not relevant to those of you doing the adjusted syllabus in 2020. 4 on 625 equals 5 times x cubed minus x to the power of 4. Okay, it's just between 0 and 5. Find the mean lifespan of the Lorenz wing butterfly. Okay, so the expected value of x, or the mean, is the integral over the domain, which is 0 to 5 of x times f of x. Okay, so shift plus 0 to 5 of x times f of x with respect to x. And that is 10 on 3. Always answer exactly, so yes, you can write that as 3.3 recurring, but you cannot write that as 3.33. Just leave it as a fraction. There's no reason to hit Control Enter at all. Just leave it as a fraction. And that's weeks. 10 on 3 weeks is the average lifespan of the butterfly. In a sample of 80 Lorenz wing butterflies, how many butterflies are expected to live longer than 2 weeks, correct to the nearest integer? Okay, so we first of all want the probability that a butterfly's lifespan will be more than 2 weeks. Okay, so to do that, that's going to be the integral from 2 to 5 of f of x. So shift plus integral from 2 to 5 of f of x is 2853 on 3125. And then we have 80 butterflies, so how many of them? And so then it will be the number of butterflies that live that long will be that probability, 2853 over 3125 times 80. Times 80. Okay, and we want nearest integer because they are butterflies, so to the nearest integer, so I pressed Control Enter to get as a decimal, to the nearest integer, that is approximately 73 butterflies. Okay, what is the probability that a Lorenz birdwing butterfly lives for at least 4 weeks, given that it lives for at least 2 weeks, correct to 4 decimal places? Okay, so we want the probability that x is bigger, at least 4, so bigger than or equal to 4, given that it's bigger than or equal to 2. So we need the intersection of those two things. If x has to be both bigger than or equal to 4 and bigger than or equal to 2, that is just x bigger than or equal to 4 over probability that x is bigger than or equal to 2. Note that in a continuous random variable, the probability that x is bigger than or equal to 2 is the same as the probability that x is bigger than 2, so that's simply going to be that. And so all we have here is the integral from 4 to 5 of the function for the probability that x is bigger than or equal to 4, divided by the answer that we've got up here, 2853 over 3125. Okay, so just going to edit this integral we did up here. So integral from 4 to 5, is that. So we want that answer divided by this answer, which is 821 on 2853. The question asks for 4 decimal places, so Control Enter is approximately 0.3152. Oh, sorry, I made a mistake with the decimal there. When I hit Control Enter, it did the division again by a different fraction. Sorry, so I actually want to work out what that value is, corrected 4 decimal places, which is not 0.3152, it's 0.2627. Apologies, yeah, that was an error, that calculation there. Okay, so 0.2627, correct to 4 decimal places. Okay. The wingspan of Lorenz birdwing butterflies in town A are normally distributed with a mean of 14.1 centimetres and a standard deviation of 2.1 centimetres. Find the probability that a randomly selected Lorenz birdwing butterfly in town A has a wingspan between 16 and 18 centimetres, correct to 4 decimal places. Okay, so this is on the syllabus for 2020, so you can all answer these couple of questions. What are we going to say? W is the wingspan in centimetres. W is distributed normally with a mean of 14.1 and a standard deviation of 2.1, so variance of 2.1 squared. And so then the probability that W is between, so bigger than 16 and less than 18, correct to 4 decimal places. Okay, so menu 552 for normal CDF. Lower bound is 16, upper bound is 18, mean is 14.1, standard deviation is 2.1. Okay, 4 decimal places, so that is 0.1512, correct to 4 decimal places. A Lorenz birdwing butterfly is considered to be very small if its wingspan is in the smallest 5% of all the Lorenz birdwing butterflies in town A. Find the greatest possible wingspan in centimetres for a very small Lorenz birdwing butterfly in town A, correct to 1 decimal place. Okay, so this would be where the probability of the wingspan being less than a particular value has to be 0.05. So we're going to use inverse normal, so menu 553. The area is 0.05, the mean is 14.1, and the standard deviation is 2.1. Okay, and so that tells us that A is approximately 10 point, 1 decimal place, 6. Okay. So very small butterflies have wingspan less than or equal to 10.6 centimetres. So the greatest possible wingspan is 10.6 centimetres. Okay. Each year, a detailed study is conducted on a random sample of 36 Lorenz birdwing butterflies in town A. A Lorenz birdwing butterfly is considered to be very large if its wingspan is greater than 17.5 centimetres. The probability that the wingspan of any Lorenz birdwing butterfly in town A is greater than 17.5 centimetres is 0.0527, correct to 4 decimal places. Find the probability that 3 or more of the butterflies in a random sample of 36 butterflies from town A are very large, correct to 4 decimal places. Okay, so we could have been asked to work out that probability. So that would be menu 552, the probability that a wingspan is greater than 17.5 centimetres. Oh, sorry. However, the question is giving you that value so that you all have the right value to move on. So you can work that value out, but if they'd asked you to find it and then to use it, the risk is that some people are using the wrong value and still doing all the correct working after that. So they're giving you that value. Therefore, I would use that value rounded as it's been given to you, because those answers would all be accepted as correct in this instance. Okay, part 1. Find the probability that 3 or more of the butterflies. Okay, so now we've got a binomial situation. Okay, so now I'm going to say X is the number of very large butterflies. and x is now a binomial variable, and we have a sample of 36 butterflies, so n is 36, and there is a probability of 0.0527 that they have very large wingspan. And so we want, in this case, find the probability that 3 or more of the butterflies, so probability that x is bigger than or equal to 3. Okay, so menu 55B, we have 36 butterflies, probability of success is 0.0527, lower bound is 3, upper bound is 36. So that is 0.2947. Okay, part 2. The probability that n or more butterflies in a random sample of 36 butterflies from town A are very large is less than 1%. Find the smallest value of n where n is an integer. Okay, so this time you know the probability that x is bigger than or equal to n is less than 1%. Okay, so I don't like that they called this n because it's not n in the binomial distribution. You still know that n is 36, okay, in terms of the binomial distribution. We essentially want to know what does this number have to be so that this probability is now less than 0.01. So we know if that number is 3, the probability is about 0.3. So it's way too big. So all I would simply do here is use trial and error, okay? You can have a look at, all right, when n equals, if n is 4, bigger than or equal to 4 is about 10%. Probability that 5 or more butterflies have a very large wingspan is about 4%. Probability that 6 or more butterflies have a wingspan is, it is 0.01 to correct to 2 decimal places, but it's still slightly more than 0.01, and you want that value to be less than 1%. So we're going to have to go one more, I think, to say that n must be 7. Yes. And then anything bigger than that will obviously also be less than 1%. So we're trying to find the smallest value of n, so n equals 7 is the smallest value. Okay, so we know the probability that x is bigger than or equal to 7 is equal to 0.024. In fact, I might give both of them just so I can justify that that's the smallest value. So probability that x is bigger than or equal to 6 is equal to 0.0107, and this is 0.244. Okay, so therefore n equals 7 is smallest value. Okay, part 3 here, now we're getting into the statistical inference, so this is not relevant to question to 2020. So for random samples of 36 butterflies in town A, p hat is the random variable that represents the proportion of butterflies that are very large. Find the expected value and the standard deviation of p hat. Okay, so we know that the expected value of p hat is just p, which in this case is we're given p, what was it? 0.0527. Okay, and we know that the standard deviation of p hat is the square root of p times 1 minus p over n. You've got those formulas on your formula sheet if you need them. So expected value of p hat is p, and the standard deviation of p hat is the square root of p times 1 minus p on n. So we're simply just substituting into those formulas. Square root of 0.0527 times 1 minus 0.0527 over 36. Okay, so square root 0.0527 times 1 minus 0.0527 all over 36 is, to correct to 4 decimal places, 0.0372. Okay, so just 2 marks for those 2 answers. What is the probability that a sample proportion of butterflies that are very large lies within 1 standard deviation of 0.0527? Okay, so what we want to do is the expected value plus 1 standard deviation and the expected value minus 1 standard deviation. So 0.0527 plus that value and 0.0527 minus that value. Okay, so this means it's the probability that p hat lies between 0.0155 and 0.0899. Okay. Now we want to convert this to x. So what we need to understand here is that p hat, the proportion of butterflies, is the number of butterflies divided by 36, which means that x is 36 times p hat. So if we multiply both of these values by 36, what we actually find is that this is the same as the probability of x being between 0.5566 and 3.2378. Okay, now x is binomial and it is therefore can only take integer values. It's the number of butterflies. So if the number of butterflies has to be somewhere between those two values, then it has to be between 1 and 3 inclusive. Okay, so then menu 55B, number of trials is 36, probability of success is 0.0527, lower bound is 1, upper bound is 3. And so that probability, correct to 4 decimal places, is 0.737, okay, I have to round up, so 7380, correct to 4 decimal places. Okay, part G. The Lorenz birdwing butterfly also lives in town B. In a particular sample of Lorenz birdwing butterflies from town B, an approximate 95% confidence interval for the proportion of butterflies that are very large was calculated to be 0.0234, 0.0866, correct to 4 decimal places. Determine the sample size used in the calculation of this confidence interval. Okay, so the first thing is to recognize that P is going to be the center of that confidence interval. So P is, and we're still in non-2020 content at this point, P is so I'm going to add them together and divide them by 2 to work out the middle. 0.0234 plus 0.0866 divided by 2. 0.0234 plus 0.0866 divided by 2, which gives me 0.055. Okay, and then we know that the margin of error is going to be, well, we can do it a couple of ways. We know that let's say the bigger endpoint of the confidence interval, so 0.0866 is going to be equal to P plus 1.96 times the square root of P times 1 minus P over N. Now we know P. Now that 1.96, remember that comes from your standard normal variable. Because we want a 95% confidence interval, we calculate that value of 1.96 from that 95% confidence interval. So you can actually do that, calculate that value. Sorry, just pause the video for a minute there. You can actually calculate that value yourself, so you've got it nice and exactly on your CAS. So you can use menu 5 inverse normal 3. We want an area of 0.975, and we get a standard normal value. That's where that 1.96 comes from. So I can use that exact value by calculating it myself. I used an area of 0.975 because if I want 95% to be in here, then I want 0.25 to be down here. So less than that value has to be 0.975. Okay. So we've worked out that that value is 1.96 approximately. I'm pretty sure I've tested this before. If you just use 1.96, you will still get the correct answer in this particular question. Okay, so we know what P is as well, so we can put P into here. So we know that it's 0.0866 equals 0.055 plus 1.96 times the square root of 0.055 times 1 minus 0.055, all over n, and we can solve that for n. So let's solve. 0.0866 equals 0.055 plus this value here times the square root, the square root of 0.055 times 1 minus 0.055 over n. And we are solving that for n. Okay, and we find that n is approximately 199.95. And then obviously we can't survey 199.95 butterflies, so we have to round to the nearest whole number. Well, we have to round to a whole number, but we do just need to be a bit careful with the rounding in these instances sometimes. If you were to round n down, you wouldn't actually get 95% confidence, you'd be reducing your confidence. So we always should round up. In this instance, it means that when we round, the nearest whole number is rounding up anyway, but if we round up to 200, we will ensure that we get slightly higher than 95% confidence. Okay, and so therefore n is 200. Okay, so 200 butterflies must have been sampled to get that 95% confidence interval. Okay, so that was not relevant to those of you doing the exam in 2020. Okay, let's have a look at question 5. So we have a function. Let me define my new function. Define f of x equals 1 minus x cubed, so relatively straightforward cubic function, reflected in the x-axis and translated up by 1. The tangent to the graph of f at x equals a, where a is somewhere between 0 and 1, intersects the graph of f again at p, and intersects the horizontal axis at q. The shaded regions shown in the diagram below are bounded by the graph of f and its tangent at x equals a and the horizontal axis. Find the equation of the tangent to the graph of f at x equals a in terms of a. Okay, nice and easy with my CAS. Menu 4.9, tangent to f of x, comma, when x is equal to a. Okay, so we're just going to write that down, and it must be an equation, okay? Your CAS doesn't give you the equation, it just gives you the expression. The equation is y equals negative 3a squared times x plus 2a cubed plus 1. Make sure it's an equation. Find the x-coordinate of q in terms of a. Okay, so q is the x-intercept of the tangent, so that's going to be when 0 equals negative 3a squared x plus 2a cubed plus 1. So if we solve this equal to 0 for x, we find that x is equal to 2a cubed plus 1 over 3a squared. And we only want the x-coordinate, so that's fine. We've given that there. Find the x-coordinate of p in terms of a. Okay, so we now want to look at where does the function intersect with the tangent, which is negative 3a squared x plus 2a cubed plus 1. So we're solving our function equal to our tangent for x. Okay, and we find that happens at x equals negative 2a or x equals a. Now we already knew about the x equals a. That's where we found the tangent. And so we want the x-coordinate of p, so therefore the x-coordinate of p is x equals negative 2a. Okay, so pretty straightforward there, those first three parts. Good CAS work makes it nice and efficient. Let A be the function that determines the total area of the shaded regions. Find the rule of A in terms of A. Okay, so we want those shaded regions. Now there's a couple of ways to think about this because you've got to be careful about this region here. This is not the integral from A to whatever that q value was, 2a cubed plus 1 on 3a squared of the tangent minus, of the tangent minus f of x, because that would be including all this bit down here. It's not an area between two curves. It's the integral from a to 1 of tangent minus f of x, and then plus this bit out here, integral from 1 to whatever of the tangent. Okay, but you've got to be careful about this region here. That was where many students went wrong. Probably, to my mind, the easier way to do this would be to think about the total triangle and then taking away this bit of area under here. That's how I would do it. And you could find that as a triangle, or you could just do it as the integral of the tangent from, so remembering this is negative 2a, from negative 2a to q, which is 2a cubed plus 1 over 3a squared. So from negative 2a up to that q value of the tangent function, which gives you the area of that triangle, minus the integral from negative 2a up to 1 of f of x. Okay, that would probably be the easiest way, to my mind, of finding it. So your area is going to be the integral from negative 2a up to, now you can't write q because q is a point and you need the x coordinate of the point. So you're going to have to actually write that out, 2a cubed plus 1 on 3a squared. And again, we haven't defined the tangent as a function, so I'm going to write out that expression for the tangent, which was negative 3a squared x plus 2a cubed plus 1. Okay, so that's the area of the triangle. And then we're going to subtract the integral from, sorry, not from 0, from, let me just check, from negative 2a up to 1 of the function. Alright, so let's do that. So integral from negative 2a to 2a cubed plus 1 over negative 2a, no sorry, did the wrong thing, over 3a squared. And that's going to be our tangent. I'm going to go up here and copy the tangent. If I just press enter here, it'll go into the upper limit. So if I press Control C so that I can paste it where I want it to be, Control V. So it's the integral with respect to x of that, minus the integral from negative 2a to 1 of f of x. Okay, so that's our expression. You could write that out. You could also get it to, how do I do it? Menu 3, 9. I think if I do proper fraction, oops, it'll force it to actually kind of do that division, so you could write it that way. However you want to write it, it doesn't matter. It's the same thing. So the area is 80a to the power of 6 plus 8a cubed minus 9a squared plus 2 over 12a squared, which is the same as 20 on 3a to the power of 4 plus 2/3 a plus 1 on 6a squared minus 3/4. Whichever, you don't need to write both, just whichever. Find the value of a for which the area is a minimum. Okay, so maybe I'm going to define a new function. I can't call it a of x because it's in terms of a. Let's call it g of a equal to this, my area function. Okay, and so we want to differentiate that. So we want to do the derivative of the area with respect to a. I can't call the function in my CAS a of a because it doesn't differentiate between capital A and lowercase a, but I can write dA over on the paper. So dA equals 0, so we want to solve the derivative with respect to a of g of a, which is my area function in my CAS, sorry, g of a. We want to solve that equal to 0 for a. Okay, and we find that we get a equals negative half, or 10 to the power of, so it's 10 to the power of 2/3 on 10 to the power of 1. We could just do that subtraction, 2/3 minus 1, index laws, so it's 10 to the power of negative 1/3. Now, if we go back and have a look at here, if a were to equal, I think, what do we know about a? A has to be between 0 and 1, so actually it can't be. Let's just check that. Yeah. So I'm just going to write that one. 10 to the power of negative 1/3. Since a is somewhere between 0 and 1. I'm not sure if it was inclusive. Let me just check. No. Okay, so that's the value of a for which a is a minimum. Okay, and you can, so that was about 0.46. So if a is about 0.46, yeah, you're going to have your tangent here. So it's going to sort of do that. Okay, and apparently that minimizes our area. Right, what else have we got? Consider the regions bounded by the graph of the inverse of f, the tangent to the graph of the inverse of f at x equals b, where b is between 0 and 1 and the vertical x-axis. Okay, so let's try and think about what we know about our original function. So our original function, that's 1 and this is also 1. Oops. Sort of looks like this. And we found that when a was, so when this is 10 to the power of negative a third, that's when we get minimum area for the original function. Okay, so then we want to find the value of, so consider the regions bounded by the graph of the inverse of f. So let's now think about the inverse of f. So this is y equals f. Okay, so the inverse of f is also going to go through 0, 1 and 1, 0. But the point of inflection is here now. So we've sort of got this kind of thing happening. It's going the other way. And we want to find, so that's our inverse of f. The tangent to the graph of the inverse of f at x equals b, where b is somewhere between 0 and 1. And the vertical axis. Okay, so what we need to understand is this is essentially still the same thing. We're going to have a point where x equals b, and we're going to find the area between the function and the tangent. Function and the vertical axis this time. So what we want to understand is that this is exactly the same, and we know that we get minimum area when the x value is negative 10 to the negative a third, which means that that will happen on the inverse function when the y value is 10 to the negative 1/3. And so therefore, what we need to know here, b is going to therefore be equal to this y value here. Okay, so we're going to get minimum area when b is equal to f of 10 to the power of negative a third. Okay, so we just need to find that. So our function at 10 to the power of negative 1/3 is 9 on 10. So we get minimum area when b is equal to 9 on 10. Okay, and this is due to symmetry of f and inverse f. Okay, alright, I'm just going to erase these messy sketches down here to give me some space for this last question. Okay, find the value of the acute angle between the tangent to the graph of f and the tangent to the graph of inverse f at x equals 1. Okay, so again, let's think about so here's our function f. We want the tangent at, I've probably got that a bit steep, it's going to be hard to draw my graph. Okay, so we've got the tangent at x equals 1. Tangent to f at x equals 1 is going to be that line. Okay. And we want to know the value of the acute angle between the tangent to the graph of f and the tangent to the graph of the inverse of f at x equals 1. Now the inverse of f, remember, will have the point of inflection at 1, which means that its tangent will be vertical. Okay, so this green line is the tangent to f, and then we would have a vertical line which would be the tangent to inverse f. Okay, now we want the acute angle between those, so we want that. Okay, so we can easily enough find the equation of the tangent to f when x equals 1. So let's do menu 49. Tangent to f of x when x equals 1 is that. Okay, so this is y equals 3 minus 3x. Okay, and so therefore this is the point 0.03. So what we might do is, instead of focusing on the angle between the two curves, let's maybe focus on that. We know that distance is 3, we know that distance is 1, we can therefore find that angle in there. Okay, so we know that tan of alpha is equal to 3 over 1, so alpha is inverse tan of 3. Okay. Now, it doesn't tell us to give a rounded value. This is another thing I didn't like about this paper. You had to actually just leave your answer in terms of inverse tan of 3. And then the key thing is that theta is going to be clearly 90 degrees minus inverse tan of 3. Or obviously you could write that as pi on 2 radians minus inverse tan of 3. So again, it wasn't clear about what angle units you should be using here. So yeah, just being clear about, if you wrote 90, it should have a degree sign on it. The default angle unit is radians. So if you don't say degrees, it would mean 90 radians. The answer on the examiner's report gave this, but I don't see how 90 degrees minus inverse tan of 3 could be marked incorrect. It doesn't specify what units your angle should be given in. Okay. You could use the fact that my initial solution to this, I used the fact that gradient is tan of the angle. So if you do negative 3 equals tan of the angle, you get yourself into a bit of a mess with the negatives. It's actually just much easier to use the right angled triangles on the diagram. We obviously also could have got straight away to theta potentially by thinking about, well, this is 3 and this is 1, and saying that, well, tan of theta equals 1 on 3. And so therefore theta must be inverse tan of 1/3. So that would also be accepted as a correct answer, I would imagine. Okay, so that's the end of the 2019 exam 2.